this time around, we'll be concerned with calculations after titration. Now, the titration is done in the lab. Thereafter, every student or scholar is expected to do some calculations to determine the titre volume, the concentration of the unknown, and other calculations that is prescribed or required by the examiner. Now, in this video, we'll be concerned about the calculation of the titre volume, which is average volume of acid used, and then the calculation of the molar concentration of the unknown. Now, every titration, in particular acid-base titration, in which we are concerned in this class, you are given two reagents, two solutions. The acid can be solution A, the base can be solution B, in whatever tag the examiner might decide to tag them. One is acid, the other one is base. One must be known, the other one must be of unknown concentration. The one with the known concentration is what we call standard solution. So the student is expected to use the standard solution to determine the unknown solution. Now let's have a titration table. Now, this is a table. This is a titration table. Now, in the titration table, the values are filled. This is initial breath reading, so I call it initial reading. And this is final reading. Remember, this is breath reading. Now, we have volume of acid used. Now, at the initial reading is the volume of acid or the level of the acid in the breath before you start titration. After you have set up you have filled your acid in your breath is the initial point before you start titration. So it is filled. When it fills to 0.00, then you report it this way. Or you can decide to start from any of the points. But here in this value, assume that it was filled to the 0 mark. Now in the rough, titration was made, and then the end point, the color change occurred at 25.50. That is when the color changed. And so the breath was stopped, and as the breath was stopped, you take the reading, and let's assume that the reading was 25.50. That is wrong. Now, the volume of acid used is the difference between this and this. Now, you subtract the initial from the final. This gives you 25.50. Now, in the first titration, this is wrong. In the first titration, I refill my breath to 0 mark again. So my initial point now becomes 0.00 again. Now I titrated until when the color change occurred, I stop the breath, stop cough, and then I observe and take reading. The reading happens to be 25.00. And now the difference, the volume of acid used is the difference of this and this. I subtract the initial from the final, and then it gives me 25.00. Then the last titration. Now I refill the breath to 0 mark. So I now report my initial reading again to be 0.00. And now I titrated to end point, and I got 25.00. again. I do the difference to get the volume of acid used. It now gives me 25.00 again. Now listen, it's not a must that you must refill the burette to 0 mark. The principle is this: if after a given titration, let's say the rough titration, if the volume of acid or the volume of acid remaining in the burette is more than the volume used, it then means that the remaining volume can go another titration. In such case, you don't need to refill, you just continue. So in that case, the final burette reading of the rough will now be the initial burette reading of the first reading. But take note, if the volume used is equals to or is greater than the volume remaining in the burette, it cannot take another titration again. You are required to refill the burette before you continue. Please always take note of that. Now, in every titration table, certain things are required. These are the values. Certain things are required. You need to indicate the volume of pipettes in the titration table and also your indicator use. So now, in this case, volume of pipette. Or better still, now volume of pipette. This is the volume of pipettes used. It's 25.00 ml that was used. Now, the indicator must also be indicated. Now, indicator. The indicator use must also be stated. Now, in this case, assuming I use phenolphthalein as indicator or methyl red or methyl orange, as the case may be, you are expected to specify in the table is also required. Now, you have the titration table already with you. Very clear. After you have filled the titration table, the next thing you are expected to do, you are expected to work out what we call average volume of acid used, which is average titre volume. Now, volume of acid used, another name is the titre. Titre volume or volume of acid used is, are the same thing. Now, in this case, now we want to work. Now, having the table ready, now we can proceed to work out the average volume of acid. Now, in the workings of average volume of acid use, you are not going to include the rough, the readings at the rough. Now, you are only working with the first and the second titrations. Now, if you have done 2-3 titrations, then you are required to use the 3 titrations, but ignore the rough titration. Now, I have just 2 titrations here after the rough. So I'm going to work out average volume of acid use. That will be the sum of the volume of acid used in the first titration and the second titration. So acid used. Now, that will now be 25.00 ml plus 25.00 ml over 2. Now you are getting it clearly. Now, average volume of acid use. Now the first titration gave us 25.00 ml. That's the first titration. The second titration also gave us 25.00. This is a work of an expert. So the values happens to be exactly. It's not a must, depends on your expertise. Now somebody can titrate and have wide range, but when it is close or the same, it's a matter of your skill, how good you are in titration. So now, this is the average volume of acid use. Now you are expected to sum these two values and divide by 2. If we do that, 25.00 ml plus 25.00 ml divided by 2, the average value is going to be 25.00 ml. That will be the average titre or average volume of acid use. You now take note of that. Now, having that clear that, I would like to raise the board and then we proceed with other calculations. Let me write it down again, the average volume. Average volume of acid use 25 dot ml. Now this is noted. Now we've been able to work out average volume of acid use. Now also the pipette was used to measure the volume of the other solution, that is solution B, which is base. So now volume of pipette equals to also 25. That's the volume of the pipette used to measure the second solution, with solution B, your base. Now, having these values, now you are required to calculate the unknown concentration or the solution with the unknown concentration. Now, assuming you are given a titration and the concentration of the acid is given to you, is known, and the concentration of the base is unknown. Now, let's take for instance, now let me take the acid to be H2SO4 and the base to be NaOH, with sodium hydroxide. Now, concentration of sample A. Let me say 0.10 molar. Now, having this, now you are required to calculate this unknown concentration with a sample B. Then another thing that is very, very important, we are to look for a formula that can help us to calculate this unknown concentration. Now, you are very familiar with a formula that is CV CB VB equals to NA over NB. Now, this formula CA VA over CB VB equals to NA over NB. Now, if you are not familiar with these parameters, let's define them. CA is molar concentration of the acid, which is sample A or solution A. Then VA is the volume of sample A used, which is the volume of acid used. This is actually gotten from the average titre volume. So in this case, volume of VA is our average titre volume. Now, CB is the molar concentration of sample or solution B, which is the concentration of the base. Now, the concentration of A is given to you, concentration of sample A, 0.10 m, what is molar. Now, concentration of the base is not given, it's question mark. You have to look for it. That's what we are struggling for. Now, volume of base used is the volume of solution B measured that you added to the conical flask, which was used, which the pipette was used. Now, the volume of pipette used is 25. So, automatically, the volume of base is 25.00 ml. Now, take note of that. Then we come to Na. Na is the mole ratio between solution A and solution B. So Na is the mole ratio of solution A. Then Nb is the mole ratio in solution B. This can actually be gotten only from the balanced chemical equation. You must know the reactants, their chemical formulas, and then you write a complete balanced chemical equation. Then with that, you're able to determine the Na value and the Nb values. So at this point, let's write the chemical equation and balance it to know the Na value and the Nb values. Now, it's very, very important. Let's take that the reactants are H2SO4, that is sample A. Let me see. Sample A is H2SO4, and then let me say sample B is NaOH. Sample B is NOOH. Now, if these are the two samples, then now you are required to write a chemical equations where reactants at the left hand side, the products at the right hand side. Now, being acid-base titration, the reactants acid and base react, it can only produce salt and water. And when two reactants react and produce acid and base react and produce salt and water, that reaction is called neutralization reaction. Neutralization reaction is a reaction whose reactants are acid and base, and the product are salt and water. Please take note of that also. Now, I would like to write a balanced chemical equation. Now let's take SO4 plus NaOH. It produces Na2O4 plus water. Now, this is the, okay, this 4 here. Now, this is the chemical equation. Now, after you've written this, you are written the reactants out and the product. Now, what the next thing you are expected to do, you look at the atoms or the elements in the equation, and to make sure the elements or the atoms at the right hand side are equal with the atoms at the left hand side. Now, this sign stroke means it's a process. This arrow pointing to the right is a process. This process indicates process, but this left hand side and the right hand side must be equal. So it also means equal. This left hand side is equal to the right hand side. That's what it also signifies. So if it is equal, that is what we call the law of mass conservation in chemistry. Now, if it is equal, we need to look at elements, atom by atom, to verify if they are actually equal. Now, when you are balancing chemical equations, take them atom by atom. Take them atom by atom, or to say element by element. Now, let me take hydrogen. Now, hydrogen here has 2 hydrogen. Now, here 1. So 2 plus 1 is 3. Now, how many hydrogen do I have at the right hand side? I have 2 hydrogen. Here I have both sides. Here 1, here 1. I have 3 hydrogen. It's not balanced. So what I will first do, I will going to increase this. See how I can increase the right hand side if I can increase it to be equal with the left hand side. So to increase it, let me add 2 here. I add 2 here. Let me write it very clearly. Now, 2 here. This now makes here 4, because this, now also take note please, when you have a number like this is a subscript. Now it affects only these elements. Now, but if you have this subscript 2 affects only this element. But if you have an integer, this is an integer. If you have an integer in front of the compound, it affects the whole of the compound. All the elements in the compound are affected. Now, this means that this is 2 times 2, this 4 hydrogen, while this is just 2 oxygen, because this affects this. Now, take note of that whenever you're doing balancing chemical equation. Also, when you are balancing chemical equation, after you have written the reactant and you have written out the product, don't at any time attempt to alter. Don't at any time attempt to alter the subscripts. When you alter the subscripts, you will alter the identity of that compound. You alter the identity of that compound. Now, if I am looking for a way to indicate that oxygen is 2, and I decide in this water molecule, I decide to add 2 there. Now, with the intention that I want to indicate 2 atoms of oxygen. Now, it has altered the identity of the compound water, or the molecule water. Now, this is no longer water, it's now hydrogen peroxide. So don't attempt to ever alter the subscripts. Only the integers that can be changed to balance the chemical equation. So here I have 4 hydrogen, here I have 2, here I have 1. So to balance it, to make this side 4 also, I now add 2 here. Now, I've added 2 here. Now, these 2 affect the whole of this compound. So now, this is now 2 hydrogen. Now, plus these 2 hydrogen, I now have 4 hydrogen. Here, 4 hydrogen. Now, for hydrogen is now balanced. I now come for sulfur. We have 1 sulfur here. How many sulfur do we have here? We just have 1. So sulfur is balanced. I come to oxygen. Oxygen, how many oxygen do we have here? 4. Here this affects this. So this is 2 oxygen. So there's 6 put together. Then how many do we have here? Here we have 4. And then here we have 2. We have 6 oxygen. Now, oxygen is also balanced. It then means that in this chemical equation, we have both sides balanced. So this is a balanced chemical equation. But the chemical equation is not complete without indicating the states. The states of the various reactants and the product. You must state them. Whether it's liquid state, whether it's gas, whether it's aqueous, gaseous, aqueous, or liquid state. Now, so we need to also take notes. Of certain things that are very key. When it is liquid, you are expected to just indicate small letter L. When it is gaseous, you are expected to just indicate small letter Z. Now, if it is when it is aqueous, you are expected to write small letter AQ. These are the specifications. Now, you know when we say aqueous, it then means that that particular reagent or that compound is dissolved in water. That is aqueous. Whether it's that particular reagent or the compound, the product or reactant is liquid at room temperature temperature at its pure state, or whether it's gaseous, or whether it is solid. If it is dissolved in water, it is referred to as aqueous state. Take note of that. Now, the solution you use, the tetraozosulfate 6 acid that you use, is a dilute solution. It's dilute solution because it's dissolved in water. It's dissolved in water. It's diluted in water. So in that case, it is aqueous because a certain amount of the acid in water is dilute solution. So it's aqueous. So you indicate small letter KQ. Then you come to sodium hydroxide. Now, sodium hydroxide, which is solution B given to you, is also prepared with water. It's dissolved in water, so it's also aqueous. So you write AQ also. Then, now you come to the product. These two reactants reacted and gave this product. And this product, after the reaction, the end of the titration, in the conical flask, you did not see any solid. It is still solution, clear solution, no precipitate formed. It means that the product is also soluble in water, soluble in aqueous medium. So that product is also aqueous. So you indicate also aqueous. Now, water. The state of water is liquid. So small letter L in bracket. Small letter L in bracket. Now, this indication of states must be written in form of subscripts. It must be stated in form of subscripts. Write it down below the same level with the subscript numbers. Now, they are written as subscripts. Don't write it as like the same level with the elements. Now, take note. If you write it this way, you are interested to write this is water. Now you want to indicate the state. You decide that this small letter L in bracket, you say you are indicating states. This is not subscripts. It's not subscripts, so this indication is wrong. It's not an indication of states. Rather, what you are expected to do, let it be written in subscript form. In subscript form. This is how it's supposed to be written. Now, having said that, now it's very clear. Now we have a balanced chemical equation. Now we can look at the mole ratio. What is the mole ratio? In this reaction, now 1 mole of H2SO4 reacted with 2 moles of sodium hydroxide to produce 1 mole of sodium sulfate and 2 moles of water. Now, so the mole ratio is 1 to 1 into 2. So 1 mole of H2SO4 reacted with 2 moles of sodium hydroxide. I come again, 1 mole of solution A, 2 mole of solution B. Now, give this product. Now, in that case, we'll be able to know what is A and what is B. So in this case, A being ratio of the acid will now we say is equals to 1. Equals to 1. Then NB is equal to 2 because the sodium hydroxide, which is solution B, contributed 2 mole for this reaction. Now with this, we now have all the parameters in this formula which we can use to work out the unknown concentration. What we're expected to do, we know this, we also know this, and this is what we don't know. This is what we don't know. The molar concentration of B is what we don't know, which is indicated here earlier. So we'll now make CB the subject of the formula, then work out and determine the concentration of the unknown. Now, in this equation, in this formula, in this titration formula, now since all parameters are now known, it's only CB that is unknown. We make CB the subject of the formula. If you make CB the subject of the formula, we're going to have CB equals to CAVA over, this was the meaning, VB, this multiply this cross multiplication, this will come to this, this will come to this. So this will be NB and this will be NA. Now this we've been able to successfully make CB the subject of the formula. Now we can now do substitution of values. Now what is concentration CA? Concentration of solution A. Concentration of solution A, we say 0.10 molar. So we now say 0.10 molar times. What is the volume? Volume of solution A used is our titre volume, which is the volume of acid used, 25. So 25.00 ml. Now what is our mole ratio of the base, which is NB? We have said it was equal in a balanced chemical equation, that was equal to 2. So we now say times 2. Now all over, we come to our volume of base, volume of solution B, which is the base, is the volume of pipette used, which is 25 ml. Please, you see me indicating the units alongside. Indicate the units alongside. Then now Na is the mole ratio of the acid, which in that case it is 1. So times 1. Now, when you use your calculator and multiply this, divide by this, you will now arrive at what we call equals to 0.20 molar. Now, concentration of solution B, which is our base. This is how you calculate the unknown concentration in titration. Now, what we have just done, we took solution B, the base, to be of unknown concentration. Some other time, it is the acid, it can be. Now, sometimes some other questions can be asked as student for you to manipulate to arrive at answer when you have the good details of how titration calculations are handled. In any time, it's a must that you are going to be provided with the concentration of one solution, while the concentration of the other will be unknown. You have the headache to determine that. Now, having noted this, I think we can summarize with this calculation by letting you know that unit indications are very, very important. The unit must be carried along in the calculations and then arrive at the right unit. Now, look at the units. Here, this unit, ml volume, cancel with this. Now, this is the only volume remaining. That is why, at the end of the day, it's still reflecting here. This is the only unit remaining. That's why it's reflecting here. So it reflects in the answer. Now, some students, what they do, they don't carry the unit along. They will just be writing values. Like here, if they are doing it now, they will not write the unit of the concentration. They are not going to write the unit of the volume there. They don't write the unit of volume here. They just do multiplying and dividing values